Welcome to this video on the nature of econometrics and economic data. Where are we in the course? We are in the very beginning. The course has two parts and each part has various chapters. These chapters are the chapters in Wooldridge's book Introductory Econometrics. So I'm following this structure there. In part one, we talk about the basics of regression analysis, and in part two we cover some advanced topics. This video here is on chapter 1, the nature of econometrics and economic data, as I said. Econometrics is almost everywhere, and I'm just going to start here with some examples of actually questions that can be studied using econometric methods. So where econometrics has something to add. Obviously, if we really want to study these questions, we have to look at them from various angles. But oftentimes, it's actually very powerful to use econometric tools, as I will try to convince you in this course. So the first question is, will a corporate tax cut benefit the middle class? This is an empirical question, and you can say something about it by using econometric methods. The second example is about multipliers that you might know from macroeconomic models, and what one may want to do is to measure these multipliers in order to make better predictions and in order to judge whether government spending should, for instance, increase. One can also study questions related to individual decisions. So here the question is, should I have my baby at home or should I give birth in a hospital? And also here we can use econometric methods to say something about that question. One can study new markets such as eBay. So here the title is Market Transparency, Adverse Selection, and Moral Hazard. The question is, what does it do to seller behavior when you increase transparency on the market by introducing a feedback system. Feedback system is common on many platforms nowadays. Another question that can be studied using econometric methods is the relationship between class size, the number of years of education that are attained by individuals, and wages. So what does it do to individuals if you decrease class size so that there are less students per teacher? Does it lead to more education, better educational outcomes? Does it lead to higher wages later in life? Another question that can be studied. And also one can look into a bit more special questions like the price elasticity of hard drugs. The case of opium in the Dutch East Indies. So the question here is simply, what does it do to the demand for drugs when prices increase? And here, as you can see, historic data are used to answer these questions, again, using econometric methods. Yet another question is, what is the effect of advertising on website visits, right? What you see here in this plot is taken from a paper by Varian in 2014, and you see basically this curve here, this solid line. So the solid line are actual website visits, and the dashed line are predicted website visits for a situation that has actually not happened, namely the situation without advertising. So the difference between those two curves, that would be the effect of advertising. And it turns out that nowadays one can actually measure this effect very well, which has led to an explosion, let's say, of online advertising markets. There's a lot of spending online. So a lot of advertising is moving from traditional TV, radio to online, as you know. And finally, a topic in economics that's very, very classical, adverse selection, moral hazard. Can one actually use empirical data, empirical analysis, to say something about that? So how much of behavior is adverse selection and how much is moral hazard? Can one use data to say something about that? Again, one would use an econometric analysis with these data to answer this question. Now, in the following, I want to talk about these 4 subtopics on this slide here. And I want to start with the first one, which is the question, what is actually econometrics? And one way to say something about this is to look at a classic quote by Ragnar Frisch. He won the Nobel Prize in 1969. And he did actually define econometrics in 1933 in the editorial of Econometrica. This was actually the first issue of Econometrica, and Econometrica is the best journal for work in econometrics. So it's extremely prestigious to publish in there. And in this very first issue in the editorial, he made an attempt to define econometrics, and this attempt was very good because I'm citing it here, at least in my eyes. So I'm going to read to you this quote. But there are several aspects of the quantitative approach to economics, and no single one of these aspects, taken by itself, should be confounded with econometrics. Thus, econometrics is by no means the same as economic statistics, nor is it identical with what we call general economic theory, although a considerable portion of this theory has a definitely quantitative character. Nor should econometrics be taken as synonymous with the application of mathematics to economics. Experience has shown that each of these 3 viewpoints, that of statistics, economic theory, and mathematics, is necessary, but not by itself a sufficient condition for a real understanding of the quantitative relations in modern economic life. It is the unification of all 3 that is powerful, and it is this unification that constitutes econometrics. So basically what he's saying is that econometrics is not simply something like applied statistics, right? Econometrics is not something like a form of economic theory. It's not about economic statistics, right? So these time series things that you see in the news. No, econometrics is something that you get when you bring all these things together, and then use the insights you get from this in order to look at economic relationships. And one word that appears here already is quantification. So quantification is very, very important, and we will get back to that quite a few times. Economic theory often says, something will increase when I change something else, right? But in real life, what is often important is that you know by how much something will increase. And theory can normally not tell you anything about that. So this quantification is really, really important in real life, and this is something we will definitely come back to. Now, he actually continues, and he says something that is quite interesting. in the context of what we've seen over the last 20 years. So when you look at Silicon Valley, then big data and AI and deep learning, etc., are really very important concepts, right? But and they create a lot of money, let's say, because with big data you can do amazing things, and people value them, and they pay for them in one way or another. But Ragnar Frisch, he warned that big data alone is not enough, and he said that basically we need econometrics to make the most use of big data. So there's a very nice quote that I want to share with you too. So he says, this unification is more necessary today than at any previous stage in economics. Statistical information is currently accumulating at an unprecedented rate, but no amount of statistical information, however complete and exact, can by itself explain economic phenomena. If we are not to get lost in the overwhelming, bewildering mass of statistical data that are now becoming available, we need the guidance and help of a powerful theoretical framework. Without this, no significant interpretation and coordination of our observations will be possible. So what Ragnar Frisch is basically saying is that you should think before you do an empirical analysis, before you look at data. And this is exactly what econometrics is there for. In some sense, it's a formalization of our thinking. It helps us to make up our minds before we even open that data sets, and to think about the steps we want to take to discipline us. And this is tremendously useful. Even though we will not study all these very fancy methods that are now employed, the basic insights we will still have in this course. So the basic insights will be there even for that very simple linear model that we will study. Good. So what is econometrics? One way to put it is to say, econometrics combines economic theory and mathematical statistics to analyze economic relationships, test economic theories, and evaluate government or business policies. A distinguishing feature of econometrics is that it focuses on problems associated with analyzing non-experimental or observational data. These are data that simply were generated by people doing things, let's say, right? So you let people do things, and then you record what they do, and then you have data. These are called non-experimental because nobody has experimented. What does it mean to experiment? Experimenting means that you tell one group, look, you're going to act in this condition, and you tell another group you're going to act in that other condition. So you're going to say, you guys, you get to go to college, and the other ones you say you are not allowed to go to college. So the first one, they must go to college, and the second one, they are not allowed to go to college. And then you look at what happens to people. This would be an experiment. And obviously, this example already shows you that we cannot always run experiments. So we have to use these observational data to learn something about underlying relationships. And the last point I put here is that sometimes policy changes can be considered a national experiment. And we're going to talk about that later in the course as well. So a natural experiment is an experiment that sort of happened by chance. But the distinguishing feature, or a distinguishing feature, a very important one, is that econometrics is all about non-experimental or observational data. And when you look at statistics, to a large extent, statistics has nothing to say about this. It is here that econometrics really makes a contribution. Good. So this brings us to the second part of this video. What are the steps in an empirical economic analysis. So if I want to make a bit of a plan, how would I split this up in steps? So first of all, an empirical analysis is about using data. And in the background, there's some sort of a hypothesis or a theory that one wants to test, bring to the data, or one wants to estimate some relationship that is of interest. So that relationship could be something like, from a firm's perspective, how much is the effect of an increase in the price of my product on demand for that product. So that would be simply a relationship of interest. And once I know that relationship of interest, I know a bit better how I should set my price, right? So you can split this up in steps. So step one would be to formulate your question of interest. So you're not starting and say, oh, I have some data, I check, what is in there, and then let's see what I can learn from it. No, you should start with a question that you're really interested in. Then from that question, you come in step two to formulating an econometric model. So sometimes you can use a formal economic theory model. Sometimes you would simply postulate a relationship. Then once you have that model formalized and formulated, you can formulate hypotheses that you're interested in. And you are now able to formulate them in terms of the unknown model parameters. After that, you collect data, you download data, or you find some smart way of collecting them. And you use econometric models to estimate the parameters of the econometric model and then formally test the hypotheses of interest. Step 5 is very important. Step 4 gives you some formal results. Step 5 is leaning back and carefully interpreting the results. A bigger picture, a more encompassing way to look at them. And the guiding question is, are they somehow meaningful? Are they economically meaningful? Do they make sense? Some more detail. So step 1, formulation of the question of interest. So here are just some example questions you might be interested in. Does an increase of the VAT, value-added tax, on gasoline have an impact on gasoline consumption? A policymaker might want to know that, because it's all about who's paying basically that tax incidence you might have heard about in your micro theory course. And of course, welfare effects are related to how much demand reacts. So if demand doesn't react, then you could argue that welfare doesn't really change, because you don't have these inefficiencies arising that you know from the theory of taxation. Second example question: does job training have an impact on worker productivity? Does it actually do something? That's interesting to know, because we put a lot of money into these job training programs, so we might want to actually measure the effect they have in order to judge whether that money is well spent. Third question: does an additional year of schooling have an impact on one's wage? What that is related to is the question, should we try to encourage more people to get more schooling? Or is it actually the fact that if we send them to school for longer, then this is not really rewarded in the labor market in terms of the wage? So in a wage, in the back of one's mind, one would think of the wage as also reflecting a worker's productivity. So those who are more productive, they would earn higher wages. And last question here: is there an impact of legalized abortion on crime? That's a question that is hotly debated. and people have opinions about that question, but one might want to bring some empirical evidence to the table to make a step forward. Sometimes what we do is we construct a formal economic model and let that help us to formulate our question of interest. So an example of a formal economic model could be a demand model. So demand theory assumes that individuals allocate their budget to a set of goods so that they maximize their utility for a given set of prices. So the theory says, you know, I'm going to choose my quantities, my quantities Q1 up to QK, so that I maximize my utility, which is defined on these K quantities, such that the budget constraint is satisfied. So the budget constraint is that my spending, which is the K prices multiplied by the respective quantities and added up, is less than or equal than my budget. That's very, it's almost tautological, but this is the way economics thinks of demand. From this, we would get a system of demand equations that relate the quantity consumed of goods to the consumer's budget, to prices, and to individual characteristics that would affect taste. So I'm going to get my demand functions from this. So Q1 up to QK, these are functions, F1 up to Fk, of the budget, the prices, and individual characteristics. And I could take that as a starting point to do an econometric analysis of the impact of an increase in the VAT on gasoline on the consumption of gasoline and other goods, because that tax will basically affect all demands, right? And I could use theory to guide me when specifying these relationships. So how Qs relate to X and the Ps and age and education, in order to then estimate parameters of interest, and then I can even use my theory to say something about welfare effects. And what you see already here is that each of the K demands will in general depend on all prices. So I need to specify my empirical relationships in that way, right? So the Qs should always depend on all the Ps. But I don't always have to use a formal economic theory model, right? So sometimes I can just resort to intuition. So a labor economist is interested in the effect of job training on worker productivity, for instance, and basic economic understanding is sufficient to realize that factors like education, experience, and training affect worker productivity. So, and as I said before, workers, we can think of them as being paid according to their productivity, so that there is a positive relationship at least. So what that means is that there must be a model that looks more or less like this here. So the wage that somebody earns is a function of his education, his experience on the job, and whether or not that person has received any additional training. Good. So that concludes step 1. Step 2 is the formulation of an econometric model. When we do that, then what we have to do is we really have to write down a functional form of, for instance, these demand equations or the wage equation. One has to take a stance and make a decision on how to deal with variables that one would love to put into that model, but that are simply not observed, that are not part of our data set. So an example of an econometric model to analyze the impact of training on worker productivity would be this one here. So one says that the wage is a function of how much education that person has received, the experience that person has on the labor market, so how long that person has gained experience doing that task, whether that person has received any formal training, and some extra stuff, which is collected in this term plus U. So all these factors are entering additively, and you see also these betas here, right? Beta naught, beta 1, beta 2, beta 3. So by the way, I'm saying beta naught for beta 0. This is a common way to refer to it. Simply, yeah, just to clarify that so that you don't get confused. And then you have these 4 parameters, in addition you have this U, and the U is the error term. Okay. And sometimes the error term is also called the disturbance term. This disturbance term will play a very important role in our discussion throughout the course, actually. Good. So once we have our econometric model formulated, what we want to do is we want to formulate hypotheses in terms of the unknown model parameters. So these would be the betas in my model. So we may, for instance, hypothesize that an increase of VAT on gasoline decreases gasoline consumption. So there would be a negative effect. So it would be normally in an econometric model a negative beta, basically. We may want to hypothesize that training increases a worker's wage. That would be a positive coefficient on training. Here in the model on the previous slide, this would mean that beta 3 would be positive in the wage equation. The next step then is to collect data and to use econometric methods to estimate the parameters in the econometric model and formally test the hypotheses of interest. Nowadays, it's actually the case that a lot of data can be found online. So think of platforms like Kaggle, where firms just put data sets so that others can play around with them. Think of institutions putting data out, like Statistics Netherlands. So they have lots of data actually on the web, etc., etc. Here on campus, we have Center Data. You can go to the website and simply download data from the list panel. The list panel is a panel data set, and I'm going to talk about what that means. It's a data set for individuals in the Netherlands, and they're asked every few weeks about all kinds of things, and you can just download the data and analyze them. So there's a lot of data available. It's less and less of a scarce factor for empirical analysis. But of course, we need to find the relevant data for the question of interest. For the questions I talked about before, that would be data on individuals' consumption of a set of goods and at the same time prices, budgets, and characteristics of these individuals. Or data on workers' wages, education, and experience and training, whether they received any training. Once you have your data set downloaded and put together, you're going to use econometric methods, and this is ultimately what we're going to learn about in this course here, to estimate the parameters of interest and then to formally test hypotheses of interest. You can also use these models, of course, to make predictions. One prediction would be the change in consumption due to the impact of VAT or a VAT increase, or you could forecast, for instance, unemployment, GDP, inflation, etc. And here you see already, like, these forecasts are really, really important in practice. Think of a bank. A bank is really, really interested in forecasting how these quantities will evolve, because the bank has to somehow take that into account when making important choices. Finally, step 5. So here I said before that one leans back, and one looks at the results and asks oneself, do they make sense? So carefully interpreting the results is really, really important, and judging, are they economically meaningful? Do they make sense? What, and very much related to that, what do the magnitudes actually mean? Do these magnitudes actually make sense? So it's not sufficient just to conclude that something is statistically significant or significantly different from zero. No, you wanna look at what is called the point estimate, the estimate of your quantity of interest, of your coefficient of interest, and you wanna ask the question, does that make sense? Often a very a good way to proceed is to not look at statistical significance, but to look at confidence intervals. Yeah, this brings us to the third part of this video here. This is an overview over how the way data are structured. So I already mentioned briefly panel data, so we're going to now see what I meant by this. So the most important economic data structures are cross-sectional data, time series data, pooled cross-sections, and panel or longitudinal data. What are cross-sectional data? So first of all, before I get into the details, you would normally use the plural for data, right? So it's a data set, but the data are available or something like this. So what are cross-sectional data? A cross-sectional data set consists of a sample of individuals, households, firms, countries, etc., at a given point in time. So you get many units, right? For instance, individuals at one point in time. And you get data for those. What we'll normally do is to assume, or in the best case, we can assume that these data have been obtained by random sampling from the underlying population. So there's something like a distribution function, and each data point is a draw from that distribution. Okay, and the data point consists of can be multidimensional. Sometimes, however, this assumption is not appropriate. So, for instance, suppose that we want to analyze families' wealth levels. So, you survey a sample of families, but if wealthier people are more reluctant to disclose their wealth level, then the resulting sample is not a random sample from the population of all families, because these wealthier people are going to be what we call undersampled. This is just an example of a complication where random sampling is actually not happening, and econometrics has developed many approaches for all kinds of situations you might run into that you can use, of course, to still do something about this. So to still use the data, but for each complication, basically, you have to use a tailor-made fix. But once you have understood the general principle, it's actually not so hard to do this. So that's also part of your education in econometrics to learn about this in general. And the first step is to basically develop an understanding for all kinds of complications that might arise, and I will do my best to help you with that. Once you have cross-sectional data, since these are all, in the ideal situation, you have random sampling, and then the ordering of the data actually doesn't matter, right? So think of an Excel sheet. Each row is one data point for one individual, let's say. Then you can just do a permutation of the rows. You can just reorder all the rows and what has been in row 5 is now in row 10. Doesn't matter, because the observation number is meaningless. So in that sense, the ordering of the data does not matter. How do cross-sectional data look like? It's often useful to look at what you can call the key, right? So the key in this data set is the observation number, and here the observation number would be individual. And then you have, so again, think of this as an Excel data Excel sheet, right? So in the rows you basically have the individuals, okay, and then you have variables for them, like a wage. Another data set would be for countries, right? So for each country you have one observation, and then you have various variables for these countries. Many macro data can be found online, so they're great websites for that. Or for that matter, great websites where you can find COVID data, right? COVID related on infections, vaccinations, etc., etc. So loads of data are available online, but here macro data for countries at a given point in time. As another example. Time series data. So time series data have observations on a variable, one or several variables over time. So think here of examples like stock prices, money supply, GDP, gross domestic product, annual homicide rates, automobile sales, etc. So stuff that is recorded over time. The difficulty here is, and we're going to cover this, of course, later in the course, that you cannot think of observations as independent over time, right? So GDP of last quarter is very similar to GDP of this current quarter. Normally it's quite the opposite, right? A simple model predicting next quarter's GDP growth to this quarter's GDP growth actually works really well. So what is happening now is actually a good predictor of what will happen tomorrow. So random sampling is really not happening in the way we have it for cross-sectional data. And yes, we're going to talk about all that. So for now, just observe that time series data are very different. And for time series data, what is important is the data frequency: high frequency, low frequency, daily, weekly, monthly, quarterly, annually. On the stock market, you can have second level data, minute level data, very high frequency data. Also for many other contexts, you can have very high frequency data. For instance, I showed you before, the effect of advertising, so TV viewership or online sales, etc. You can get data at the minute level easily. Here's some examples. What you see here is, again, observation numbers, but here actually you see already that this is over time, right? These are not different individuals or something like this. This is over time a set of variables, right? For instance, the unemployment rate, right? These are time series data. Another example is the number of couples breaking up measured using Facebook updates. So this was in the New York Times in 2010. So here you see for 1 year, for each point in time, the number of breakups, right? You see that there's a sort of seasonality within the week. More breakups on Mondays, a bit more in the summer holidays, a bit more on April Fool's Day. Somebody made a bad joke, maybe, who knows? Spring break, more breakups, Valentine's Day, small hump, Christmas Day, no breakups or less breakups. However, 2 weeks before Christmas, a whole bunch of breakups. So that's an example of time series data. We're going to see that again when we talk about time series data. Third possible structure is pooled cross sections. So now we have seen cross-sectional data, we have seen time series data, and pooled cross-sections have both dimensions, right? So they have both cross-sectional and time series features. For instance, you have a random sample of households in 1985 with variables like income, savings, family size, etc. And then you have a new random sample of other households in 1990 with the same variables as in 1985. You get multiple cross sections over time. This is how it looks. So here you would have the first 250 observations for the year 1993, and these are housing prices. So here you see the house prices and characteristics that played a role at that point. And the environment, so the property tax at that time, square feet, etc., size of the house. And then from 251 onward up to 520 observation number, you have data for 1995. So again, a cross-section of house prices. Finally, panel data, closely related but a bit different. So panel data set consists of a time series for each cross-sectional member in the data set. So for instance, you would have a random sample of older individuals in 2004 with variables like income, savings, health, etc. And the same set of older individuals is surveyed again in 2006, 8, 10, etc. So on the way you might lose some of them because they drop out of the sample, they don't answer anymore, or they die. But it's the same households over time. So the key distinction with pooled cross-sections is that the same cross-sectional units, individuals, firms, countries, etc., are followed over a given time period. Specific econometric techniques exist to analyze panel data. We're not going to really cover them here in this course, but this will come in the next step, and this course will really prepare you for that, hopefully very well. How does it look like in terms of a table? You would have, again, observation numbers up to 300, and then you have, for instance, the unit that I'm looking at here is a city, so this would be city number 1, which I observe in 86 and in 1990. And then city number 2, again in 86 and 90. And then I have like some variables over time. So murders, population in that city, unemployment rate, and the number of police. Another example would be a set of countries that I follow over time. And here I'm looking at the 10-year government bond interest rate. What you have here is time. Here was the introduction of the euro. Here was the Lehman collapse, big lender in the US. Then we have the financial crisis in the 2000s. You had all these problems with Greece. The rate for Greece increased in particular. So that's also an example of a panel data set that I'm basically visualizing or plotting here. Finally, causality and the notion of ceteris paribus in econometric analysis. This is actually very important. Usually, or very often, the economist's goal is to infer the causal effect of one variable, such as education, on another, such as worker productivity. So in contrast, an association between two or more variables may exist, but it may not be causal, right? And you've heard that before. Correlation does not imply causality, or correlation is not the same as causality. What ceteris paribus means in this context is that other factors are held constant, all else equal. So this plays a key role in a causal analysis. A correlation becomes a causal relationship when one is able to establish something like ceteris paribus. So for instance, demand analysis focuses on the effect of a price increase of a good on the quantity demanded, holding income and other prices fixed. If other factors are not held fixed, then we cannot isolate the causal effect of a price change on the quantity demanded. And we're really going to go into the details. This is not an easy topic, but it's really one of the very core topics in econometrics. We're going to devote ample attention to this. Here's just a little fun example of a paper. So the title is "Storks Deliver Babies with a p-value of 0.008." So a highly significant relationship. But obviously, this does not mean that there's this association, this correlation is very strong in the data, but it does not mean that there's a causal relationship of the number of storks on the number of babies. There's something else going on, and if we would be able to hold that something else constant in the background, then actually we would have a ceteris paribus analysis, and then we would find an effect of the number of storks on the number of babies delivered of 0, right? So the ceteris paribus effect would actually be 0. So what this all means is that the key question in most empirical studies is whether enough other factors have been held fixed to establish causality. Econometric methods can emulate such a ceteris paribus experiment way of thinking, but one has to be very, very careful. And it's often very useful to make a link with experiments. So again, as I said before, when you have experimental data, then we somehow control what's happening. So suppose we're interested in the effect of a training program for the unemployed on future earnings. So apart from training, earnings might depend on education, ability, experience, social skills, etc. So we have to hold all these things constant, which is this ceteris paribus part of everything. But in order to really learn about the effect, the causal effect of training, what we really want to do is to, at least in terms of a thought experiment, to conduct an experiment. So we would like to select a group of unemployed from the population of interest, and then assign each one of them to either the training program or not, and to then measure their earnings in some period of interest after training, some years later, right? Did the program do something to their earnings 5 years later? And we would think of these earnings as being higher when they're more productive, or when they're more likely to actually work and have a good job. Statistical methods can be used to measure the association between training and earnings, but what we really need to get right is this whole setup and the assignment. So what is really key is that we assign individuals in the right way to to the two treatment conditions, training program or not, and this will determine how useful the experiment actually is. So the key thing here is, and this is the third bullet point, if training is assigned to individuals independently of other individual characteristics that affect earnings, like ability, then the experiment is useful. So if we really randomize when we do the experiment. What would be in violation would be if we say, here are these very promising individuals, let's put them into the training program. This would not be good, because then this independence condition would be violated. And again, we're going to talk about that some more, but I think you get the idea from this already. So when we can randomize, then we can simply afterwards look at those who have been randomly assigned to the training condition and compare their earnings to the ones from individuals who have been randomly assigned to the control condition. And this is really resembling a so-called RCT, a randomized controlled trial that we know from medicine, right? So we have when we test whether some drug is actually doing its job, what we do is we give some people a random sample of people the drug, and another sample of people another random sample of people a placebo, right? Basically a pill that does nothing. And then we let them take the drug or the placebo, and we don't tell them, of course, whether they have the placebo or the drug. And then we measure what we're interested in. For instance, whether the illness is as severe as before, or whether there was some good development. Now, here in economics, or in the context of training programs, for instance, this is much harder. So there are lots and lots of practical problems that could arise. So for instance, we could simply assign people to a treatment condition like the training program, but they might not follow this advice, right? And if such practical problems happen, we have to think about, are these data still useful? And it turns out that they are. And again, econometric methods are actually very useful in this context, as we will see later in the course when we actually come back to this very example. Good. Finally, let me come back to that point that you have a lot of so-called observational data in econometrics or in the context of economic analysis. And the reason is simply that in many situations we can't experiment. Just think of college education, right? You can't really in practice tell people that they now have to go to university, or that they are now not allowed to go to university simply because you want to estimate what university education does to people. And at the same time, what is really important is to realize that those who actually choose to go to university are not directly comparable to those who choose or are forced or prevented from going to university. This means that one really has to find a good way of answering such big questions like what is the effect of college education on wages? And people have thought about these questions for a long time, and a lot of interesting and promising approaches have been developed in econometrics. So you're going to see some of that. in general, it's all about getting at causality and getting at that ceteris paribus effect that is of interest here. Let me just end with two complications and talk about them for one more minute. So when you think about the effect of college education on wages, so you could have two complications. One is that those with more education have usually less experience on the labor market. So when you look at them later in life, they've started to work later, so they have less experience on a job. So they're not comparable to those who have actually not gone, say, to university, because they have more experience, right? And at the same time, people with more ability often choose more education, right? So that's a second reason why people are not comparable between, you can't do a direct comparison between people who went to university and people who didn't. The first of the two is probably a bit easier to deal with, but already hard, or still hard. And the second one is much more difficult. So, as I said, econometrics has a lot to say about this, but ultimately, what this will bring us back to is design features of the empirical analysis. So what I called before natural experiments, policy changes. So it's all about exploiting those things, and then again, econometric methods have been developed to do exactly that. Good. So I hope that this first video has given you a bit of an idea what econometrics is all about. And in the following videos, what we're going to do is we're going to go into the details and move step by step so that you understand on a deeper level what this is all about and what all these things mean, and what you can do with data, and how you would conduct an empirical analysis. And on the way, and I find this even more important maybe, you will learn what possible complications are, and when and why you should be cautious when it comes to interpreting empirical results. With this, I'd like to close this presentation here, this video here. And yeah, all the best.